Hello, everyone. Thank you for coming my presentation. So my name is Seunghoon Hwang. I'm a postdoc researcher at Arizona State Universities. So today I'm going to talk about one of my research, quantitative characterization of human joint biomechanics using the wearable robot. And then my main research focusing on the rehabilitation applications. So before I start, I would like to thank our organizer of this workshop to provide me these opportunities. Thank you. And let's talk about first why rehabilitation is so important. One of the biggest challenges now that we have is aging populations. Because of this aging population, the number of the neurological disorders also highly increased. So currently over 3 billion people live with these neurological disorders. And then to support this patient, US government spend $800 billion annually. So that's why we need to provide a good quality of the rehabilitation to restore this patient to motor abilities and then to decrease this economic burden. Then how we provide the rehabilitation. In the traditional way, the rehabilitation is heavily relied on therapist experience and their know-how, which means we cannot provide the same quality of the rehabilitation to all the patient. And then you can see in the right video, to take care of the one patient, at least over the two therapists should be including their rehabilitation training. So this is very low ratio of the patient and therapist. So to address this limitation in the traditional rehabilitations, so many institutions and industry company develop their own rehabilitation robot, such as the Rocomet, Axo, and Harmony SHR. So these are robots allowed to automate some repetitive tasks of the therapist, and then it can also provide the same rehabilitation training by saving the predefined rehabilitation training. In our research, we also developed a wearable robot to provide a rehabilitation robot for the stroke patient. So as you can see, look at this, the patient at the first weeks. So this patient almost couldn't walk properly. Even after we are our robot, he needs extra support from us. But after 12 weeks training with our robot, we can clearly see that this patient's motor abilities significantly improve, and then now he can walk without any extra support. We also measured some gait performance from the total 13 stroke patient, and then these results also clearly show that our wearable robot can improve the patient motor abilities. But however, still, robot-aided rehabilitation outcomes still does not show significant differences compared to the conventional method, which means robot-aided rehabilitation can decrease the effort of the therapist, but in terms of the rehabilitation effect, there is no big differences. So I think we need to move forward to provide the precision rehabilitations. Then how that considering each patient biomechanics informations. Then how we provide these precision rehabilitations. So to this end, we need to have first quantitative method to objectively characterize each patient biomechanics using the wearable robot. Then we can assess the human biomechanics in more objective and in more continuous way, which means by just wearing our wearable robot, then we can assess human biomechanics every day and then everywhere. After we taking this biomechanics information, so it makes better understand how neurological disorders affecting on the human joint biomechanics in more quantitative way, not just the subjective. And then we also can utilize this biomechanics information when we develop the robotics control to provide a personalized and then targeted rehabilitation to the patient. Because if we have this biomechanics information, then robot can understand how much assistance this patient needed. And then how we assess the human biomechanics in the traditional method. So in the traditional method is so subjective, which means it depending on who is the therapist, it might be a little difference on our biomechanics assessment. So another way is to take MRI image to provide the precise the biomechanics information, but the cost of the MRI image is very expensive, and then we cannot utilize this for everyday use. So some previous study tried to quantify the human joint biomechanics, especially human joint mechanical impedance, by using the robotics platform. Especially in the shoulder joint studies, some previous study tried to quantify human shoulder joint mechanical impedance by using the robotic platform on the 2D plane. But even this research can provide valuable information, but it still have some limitation because during our daily life, we only not move on the 2D plane because we can imagine that we move in the 3D space, right? So that's why in my research, I try to characterize the human shoulder joint biomechanics in the 3D space, and especially characterize shoulder joint stiffness. Then why I focus on the joint stiffness. So human joint stability is referred to resistance against the disturbance. And then we commonly represent this stability by using the stiffness. So that's why in this research, I mainly focus on the shoulder joint stiffness. Then how we characterize this shoulder joint stiffness? So technically, by using this wearable device, we provide the input position perturbation directly on the human joint. And then during that, we also measure the output response torque. After we getting this input and output the data, so we utilize some of the system identification method to characterize this human joint stiffness or human joint mechanical impedance. And then by using this framework, I conducted two different experiments to characterize the human shoulder joint during the static posture in the 3D space, and then during the dynamic movement in the 3D space. So let's talk about first during the static posture research. So in this study, I hypothesized shoulder joint stiffness significantly influenced by the arm posture in the 3D space, which means based on our arm posture in the 3D space, then human biomechanics significantly changed. And then another hypothesis is the shoulder joint stiffness is significantly influenced by the sex differences. So in this study, to provide the position perturbations, I utilized our developed parallel mechanism shoulder exoskeleton robot, and this robot have the lower inertia on the shoulder joint, so it can provide the fast and precise the position perturbation directly on the shoulder joint, like a right video. As you can see in the right video, the robot perturbing the subject shoulder joint directly. And then we characterize this shoulder joint stiffness at 15 different posture in the 3D space. And also we collected this data from the 40 healthy individuals, including the 20 males and then 20 females. And during that, we also measure the muscle activation of the subject and then to instruct to the subject, please relax their muscles. Why? We want to more focus on the intrinsic mechanism of the shoulder joint. So after we conduct this experiment, then now we have the collected input position data and then output torque data. Then we ready to conduct the system identifications. But however, physiology system like a human joint impedance have a time varying and time invariant system characteristic at the same times. And then usually the physiology system need amount of the data to conduct the system identifications. So that's why to address these limitations, I utilized the short data, the segment system identification method developed by Dr. Ludwig at 2012. So this method, technically, I segmented total data into the short time many segments. And then at each the short time segment, this method utilized the time invariant system identifications. And then across the segment, it utilized the time varying system identifications. So after we taking these system identifications, then we can compute the impulse response function between this input position and output torque. And by using this impulse response function, then we can characterize shoulder joint stiffness. And then we conduct the process for every 15 different postures. So yeah, these are the results. As you can see in the 15 different bar graph in this plot, so we can clearly see that every 15 posture have the different shoulder joint stiffness value, which means the arm posture in the 3D space significantly influence to the shoulder joint stiffness. If we more focus on the flexion direction from the 45 to the 90 degree, flexion means the laser our arm in these directions. So then we can clearly see that when we laser our arm from the 45 to 90 degree, the shoulder joint stiffness show the decreasing trend, which means decrease the shoulder joint stability when we raise our arm in these directions. And this result also align with some anatomical studies in the shoulder joint. Shoulder joint have the humeral head and glenoid. We can simply say the ball and socket joint. So when our arm at the neutral postures, this ball is perfectly fit in this socket. So that's why to keep the stabilities. But once we raise our arm, the like X-ray image in the right, then this contact area is going to be decreased. So that's why the shoulder joint stability might decrease, such that the shoulder joint stiffness also decreasing trend. And then if we more focus on the horizontal extension fraction direction, which means the move the right and left, then results clearly show that when our arm posture at the end of the range of motion, here or here, then shoulder joint stiffness show higher value compared to the middle of the range of motions. So we can, the result also align with some anatomical characteristic in the shoulder joint, so especially for the ligament. The shoulder joint have the many ligaments, such as the glenohumeral ligament. And this ligament has some characteristics. When our arm at the middle of the range of motions, this ligament show laxity. Laxity means the less stiff. But when our arm move at the end of the range of motion in these directions, then this ligament is going to be stiff to keep the safety, because we do not this ligament prevent we move above this our range of motion. So that's why our result also show that the higher stiffness at the end of the range of motions. And then we also compare this shoulder joint stiffness value between the males, 20 males and then 20 females. And then we can clearly, you can clearly see that every 15 arm postures, males have higher stiffness value compared to the females. So this trend still stay even after we normalize on the bottom plot. So this result also align with some anatomical studies. They said the females usually have more flexible intrinsic mechanism on the shoulder joint. So that's why females show the less stiffness compared to the males. So from this research, then we can clearly, I can clearly say that by using this framework, then we can interpret some anatomical studies in more quantitative way. But this research has still limitation, because I only measure this shoulder joint stiffness during the static postures. So that's why I move on to the next research. So I characterize the shoulder joint stiffness during the dynamic movement. And then in this study, I hypothesize shoulder joint stiffness is significantly influenced the task differences, which mean during the static posture and then during the dynamic movement, shoulder joint stiffness should be different. So to make the dynamic motion, I designed the graphic user interface like the left, the figures. This graphic user interface to show the subject shoulder joint position. And then I also provide some target position and instruct to them, please reach that target. So the graphic user interface leading during the dynamic motion, the subject move up and down continuously. And then during that, our robot randomly perturb the subject shoulder joint in the orthogonal direction of the subject dynamic motions. So by using the lamp perturbation trajectories. And then we also measure the subject muscle activation by using the EMG sensor, putting on the shoulder muscles to identify how much the subjects activate their muscle activation for the specific dynamic motions. And after we finish this dynamic movement task, I also conduct the experiment to measure the static posture stiffness. So in this study, the video is not working, but I can explain. So actually, the left graphic user interface, I provide a different GUI to show the subject current muscle activation. Maybe you can slightly see over here. So on the right video, you can see the bar graph. That is the subject muscle activations. So because I measure the muscle activation during the dynamic task, I make some the range of the muscle activations. So during the static posture, if this subject can stay that muscle activation level for 2 seconds, I provide the same perturbation on the shoulder joint. And after we finish the experiment for the dynamic movement and static postures, then now we have the input position data and output the response torque data. And in this study, I utilized the second order system model with the least square fitting method to identify what is the inertia and damping and stiffness during the static posture and then during the dynamic movement. So this is the result. So as you can see in the plot A and B, that is the result of the inertia and damping. Then we can clearly see that there is no any big differences between the dynamic task and then static postures. Which makes sense because especially in the inertia is highly depending on the arm weight and then arm length. So that's why during the dynamic motion or during the static posture, subject is harder to control this value. But as you can see in the plot C, the stiffness shows significant differences between the static posture and then dynamic movement. Especially during the dynamic movement, it shows 22.6% lower than during the dynamic posture, during the static postures. So this means when we make our dynamic motions, then our shoulder joint intrinsic mechanism and then neuromotor control adjust our stiffness value to make the smooth dynamic motions. And these results also align with some anatomical study, especially in the ligament and tendon. So ligament and tendon have the stress relaxation, the properties, which mean if we provide a continuous displacement on this ligament and tendon, then it showed decrease the stiffness and decrease the stress. So this is the same as before we work out, we do stretch, right? So stretch makes our mechanism more flexible. That's why during the dynamic motion, we keep providing the displacements. So that's why it makes the less stiffness compared to the static postures. Okay, so from these two research, so I developed some control framework to characterize the human joint biomechanics by using the wearable robot. And then by using this framework, I identify how shoulder joint biomechanics changes based on the various conditions, such as the posture in the 3D space, and then based on the different tasks in the 3D space. But there are some remaining research problem we are working on, because I mainly measure this biomechanics information value from the only healthy individuals. So we are trying to utilizing this framework for the patient with neurological disorders. After we finish this, then we can compare this value directly between the healthy individual and then the stroke patient or some other neurological disorder patient. Then we can design what rehabilitation this specific the patient needed. Okay, so then from this research, I clearly show that my framework can characterize human biomechanics in more objective and more continuous way compared to the traditional assessment. Then how we utilize this value? So let's say we have the two different the patient. The one patient have the lower stiffness value compared to the healthy individual. And then another patient have higher stiffness compared to the healthy individuals. Then therapists can decide which rehabilitation needed for each patient. For example, for the lower stiffness the patient, the therapist should be provide rehabilitation can increasing their muscle strength. So then that means by using this the quantified biomechanics information, then we can design the targeted rehabilitation for each the patient. And the rehabilitation strategies can incorporating into the wearable robot and then some assistive control. Then wearable robot can understand each patient biomechanics status. Then they can decide and they can understand how much assistance the wearable need to provide for this specific patient. And then this is my research goal. To extend this research, I really want to make some single framework, not only for the patient and not only for the healthy individuals. So this framework have the diagnosis and the assistives at the same time by using the wearable robot. Then any the user just wearing their wearable robot, then we can measure biomechanics information every day and every time. Then based on that information, robot can decide the assistance for each patient or its users. That is the research goal. And then I think we can utilize this quantified biomechanics information for the assistive control. Okay, so I would like to thanks to the sponsor for my research and postdoc, and I would like to thanks to the lab member in the Hwang University in South Korea, and the Arizona State University and Northeastern Universities. And again, I would like to thanks to our organizer of this workshop to provide me these opportunities. Yeah, thank you.